folks, this is Murphy here doing a video on the first half of section 1.2, displaying quantitative data with graphs. And parallel to the first video, which dealt with a couple different types of bar graphs, some circle graphs, uh, frequency tables, two-way tables, that was all with categorical data. So now we're going to kind of move on to quantitative data as well. Talk about making and interpreting dot plots, which is a way of visualizing that data. And then before we actually move on to any other types of quantitative data graphs, we're going to actually talk about how to identify distributions and describe them and analyze them as well. So starting off nice and simply with a dot plot, it is exactly what it sounds like. It counts the frequency of things by adding dots and stacking them on top of each other, whereas the dots would represent the heights or frequency. So in this situation here, this is one that would very much be best graphed with a dot plot. Flip a coin 10 times, record the number of heads. So I have a coin here. I could flip it 10 times, and I could record the number of heads if I want to, and that would be one singular dot. If we had a graph, if we were in a classroom though, and there were, I don't know, say 25 of us, and each of us flipped a coin and then counted the number of heads that we'd have 25 dots. Some of us would have to get the same results as some other people, so we would inevitably end up stacking those dots to indicate the frequency of that outcome. I don't feel like flipping a coin 10 times the number of people that I would imagine having in a room, so what I did is I went to a simulator, random.org/coins, where it lets me choose to flip a coin 10 times or however many I want to. It even lets me choose the type of coin I want to flip. I went with a Swiss franc, because why not? And then I flipped. And this flip gets me, let's see, I count 7 out of 10 coins. So what I would do is I would jot down 7 somewhere, and I would flip again to indicate another student's coin flip, and this would be 4. And I would do this however many times I wanted to. As it turns out, I did it about 30 times, and then I recorded those numbers in an Excel document, and then I graphed them, and the graph ended up being like this. So if I were to do this, if I were to run the simulation another 30 times and then simulate another 30 sets of 10 coin flips, aka 300 coin flips, I might end up with a different outcome. I'm actually most likely going to end up with a different distribution than this, but it would still probably be very similar in the way it's described. We'll talk about the usefulness of simulations, but what it does help us recognize is the notion of sampling variability. Get used to hearing that phrase. And then I did say that every set of coin flips would probably be very similar to this in terms of how we would describe it. So then that leads to the next question. How would we describe a distribution? What are some key factors of a distribution that you would use to, suppose you wanted to describe this to someone who's not in the room, say like FaceTiming someone, and rather than tell them 2 2s and 4 3s, if you just want to describe the general appearance of this thing and what are some of its important features, what would you include? So certainly you would include the center, which we would consider to be a typical data point. A lot of people default back to the middle school notion of like mean, median, and mode, which we broaden mode to be not just the one most popular thing, but the highest cluster frequency, or the highest frequency cluster, rather. But sure, in this case, we could see that it's 5, which makes sense, right? Coin flips are 50-50. I would expect 50% of these tend to come up as heads, plus or minus a little bit, which is what this ends up showing us, right? Another thing, because there's more to this distribution than just the center, is the notion of what shape it takes. Symmetric, you can probably imagine what that is based on the root word symmetry. We'll talk about what a skewed distribution, what a uniform distribution looks like on the next page, but for now we can kind of tell that this is a distribution that's roughly symmetric. Like if I shuffled 1 or 2 of these dots around, we'd end up with something that when you folded it in half, the left half and right half would be identical. But the way we would describe this is that, yeah, 5 is the most popular thing, and then the frequency kind of peters out the further from the center we end up going. So because of that, we have rough symmetry. Another thing is the spread, right? You certainly know a measure of variability as range, but we'll talk about more advanced terminology and calculations for that in the future. But for right now, remember that the range is just the max minus the min. So because everything here goes from 2 to 8, we would have a range of 6. Which is not what the range of remember, due to sampling variability, I could end up with, like if one of my stats periods does this and gets a distribution, and then another one were to get a distribution, they might have one that looks different. They might have a different range, because really the range here is 6, but the range could be maximum 10. I could get some 0s and 10s if I went hard enough and flipped coins enough times, but they're very improbable. So flipping a coin 30 sets of times didn't happen to yield any in this case. In terms of the fourth noteworthy thing about a distribution, I imagine you might be kind of struggling to imagine what it is here because it doesn't happen to apply here. But if we did have a distribution that had some weird values, we would consider those values to be outliers or extremes. So outlier is a very particular word, and we have a mathematical way of calculating what technically qualifies as an outlier. Um, and I'm not sure if this would, but if I happen to do the simulation one more time and have a set of 31 dots and I got a 10, it's certainly noteworthy that this 10 is on its own because it has a gap in between the 8 and the 10 at 9. And I don't know how I would calculate this, but it's whether or not it's an outlier or not. Or I do know, it's just not worth doing now. But certainly it's noteworthy that it's so far greater than the rest. Even the 8 was not frequent, so to get a 10 would be certainly noteworthy and certainly worth mentioning in the description of our distribution. So, with center, shape, and spread and outliers. I'm not usually one for acronyms, so I usually ask students to come up with one. Like, all right, don't forget this. You want to come up with like a cute little word to remember it? Every year, what people come up with C, S, S, and O, yep, socks. Don't forget your socks, kids. If you're ever describing distributions, think about your socks. Center, shape, spread, and outliers. And it doesn't necessarily need to be in this order either. So I kind of saved this for last, describe the distribution of heads flips here. If I were to describe this, and if I were to exclude this point I randomly threw in here to make a point, think about how we would describe this in terms of socks. So certainly I want to note that the center is 5. I want to note that there's rough symmetry between, or of this distribution. Spread, right now we can go with range, sure. And then even the fact that there's not any outliers or gaps or extreme values, that's worth commenting on as well. So note that when I do so here, I mention the context of the problem in my description. Maybe it's too early to be talking about like how to scoop up all the AP points on the AP test for full credit, but certainly you will be losing points if in your description of a distribution, you don't mention the context of a problem. Like if someone only reads your answer without reading the question, and your answer doesn't clearly tell them what the problem is talking about, then you're not going to get credit. But look at some words that I use here to note what's going on. The distribution of heads is roughly symmetric, centered around the highest frequency of 5 heads. Yep, we know that much. All sets of 10 flips had between 2 and 8 heads, thus the range is 6. There are no outliers or gaps in the data. So I'm talking about flips, I'm talking about heads. It doesn't take too much effort to recognize that the context of this problem is coin flips. In fact, 10 of them. I even mentioned that in the problem. So this would be considered a good descriptor of distribution. Of course it was. It was done by an AP Stats teacher. It better be good. So one thing that I was a bit loosey-goosey about on the previous page was talking about the description of a distribution's shape. That one on the previous page happened to be symmetric, which is pretty easy peasy. It's when more or less the left and right half, if you were to cut in half, would be close to identical, in which case we can refer to something as either exactly symmetric if it is, or roughly symmetric if it's close enough, which a lot of things are going to be roughly symmetric and not exactly, just like I said, due to sampling variability. So a distribution with equal frequencies. Imagine I have a 10-sided die. There is such a thing, so try to imagine it. It's all the faces 1 to 10, and I roll it. If it's a fair die, then each of those faces, 1 to 10, would have a 1 in 10 chance of being rolled on. This would be the distribution for that, actually. If we pretend like the right boundaries of the bars here are the face values of the die. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, not including 0. Each of these with a 10% relative frequency. This would be called a uniform or rectangular distribution. It's uniform because every value has the same probability of occurring. Remember what a distribution is. It's the set of all of the outcomes, or the values that the variable holds, as well as the frequencies as well. So if all the frequencies are the same, it is a uniform distribution. If it's something that's a little crooked, like this dark blue and this light blue guy, we call that distribution skewed, and we would refer to the direction of the skew as well. So note that I kind of color-coded things here. The right graph is right skewed, the left graph is left skewed. And skew is basically, if I were to look at a distribution that's, pretend this is symmetric for a second, pretend that this bar is a little bit higher. If I were to take this top part of this bar that's like missing here, and maybe stretch it out so that now these values span across a greater range of values to the left of it. This would essentially be skewing the distribution to the left. We define the skewness of a distribution to be the direction that the tail goes. So this left one is skewed left, this right one is skewed right. And for reasons that we'll discuss in the future, the mean or average or even cluster is probably not the best way to describe the center of this data. The median is the go-to. So again, by the end of this chapter, we'll certainly have a good understanding of why that is. But for now, just kind of keep that fact like to the side in your brain. If I have something like this, something that has two humps, this appears to be two distributions that are kind of lumped together, right? Two symmetric distributions. We would call this bimodal. And think about why. The prefix bi meaning two, and we can see two humps here, and modal being like mode, the most frequently occurring thing. So what we have is two non-adjacent clumps or humps of data, and this usually happens if I were to have two different populations being sampled from. So today I literally just got back from the 2020 graduation, the parade that we had, and if I were to take a sample of people's ages, I'd probably get teenagers, maybe some of their younger siblings or older siblings, and then I'd probably get adults. So the ages would actually probably look something like this, maybe with different frequencies. I imagine there's more kids than, actually, I don't know. But anyway, the point is I would have two different clumps of data because I'm essentially having two different populations worth of age groups here. So that would be an instance in which I have bimodal data, and the visualization of it would look something like this. So, another thinky question. Can a distribution be more than one of these things? Can I use more than one of these terms to describe the same distribution? Think about it for a second. Hopefully when you do, you conclude that the answer is a definite yeah. Sure. I could have a bimodal distribution that's symmetric if the second hump were to have the same set of frequencies as the first one. Sure. I could have a bimodal distribution that's skewed as well as symmetric. Actually, a uniform distribution by its very nature is symmetric as well. So yeah, we can have a distribution being described by a couple of these different terms. And in fact, we should do so too if we're ever presented with one and asked to describe it. Speaking of which, I'm presenting you with a set of distributions and asking you to not just describe them, but compare them. So now it might be a good idea to actually pause the video, take a second to look at these, and if you're not going to write it down yourself, which that's fine, take a second to consider how these distributions vary and in what ways, and why that's important, and what that actually ends up telling us too. Pause it and then maybe hit play in a couple moments, but I'm going to take a brief pause in my monologue so you can do so. So if you've been considering this like I asked you to, the way you should have been thinking of it is in terms of socks. So the C in socks is center. I'm kind of splaying this out as like a bullet pointed list, but trust me, it'll be a matter of no time before you're really good at this, and then you can just kind of lay everything down in a paragraph, and it'll be a little more fluid. But just to really emphasize that I'm hitting all the key things in socks here, I'm going to label them thusly. So the center, both medians appear to be around 5 individuals per household. I'm not going to ask you to count the dots here, but what you can notice is that most of these, or rather both of these distributions happen to be centered around 5 people per household. Great. In terms of the shape, this S goes with shape. What we should notice is that this bottom one, I guess someone can make an argument for it being slightly skewed left. I'd say the range is so tiny here that it's close enough to symmetric. We can call this roughly symmetric. I wouldn't be too bothered if you called it a little bit skewed, but this one on top is certainly skewed to the right. Definitely, towards larger households. Notice I didn't just say skewed to the right, but I mentioned towards larger households. I don't know why this isn't writing. Towards larger households, because that is the context of the problem. That's what right means when I'm talking about these distributions. So in terms of outliers, or extremes, or gaps, the UK doesn't have any. And I told you there's a way to calculate it. Don't necessarily assume things are outliers, but this 26, that's way far above the rest. You can probably safely conclude that that's an outlier without any computations. But yeah, there's nothing for the UK that would be considered extreme. While there are definitely some larger sized houses of 26, and even that 15 is a bit of an oddball because of the gap here, as far as the South African households are concerned. And then the last thing here, ask yourself at least if you remember what the last letter would be and what it stands for. We did center, we did shape, we did outliers / gaps / extremes. Yeah, spread. Spread is the last one. And the only way that you know so far, I think, for describing spread is to use the range. So we could do this by excluding extreme values because that's kind of like cheating. But even if whether we do or do not, we end up with a much greater range in South African households. Without extreme values, we end up with a range of 9, and in the UK, that range is only 4. So I want you to notice something else. Not only did we describe these two distributions, but we were asked to, here we go, we were asked to compare them. If you're being asked to compare something, what you should be is looking at how the top values differ from the bottom values. AP pro tip for you. If you're being asked to compare two things, you should use language that is comparative, which means not just stating the values, but then noting which distribution has greater or lesser values regarding whatever the context of the problem is. So remember a couple things here. Remember context. That's if you ever look at an AP free response question rubric, mentioning things in context is always there. So context, comparative language, and like I said, don't forget your socks. I feel like this is a good point to conclude the first half of the 1.2a video. So hey folks, thanks for watching.